Case Study: Revolutionizing Cybersecurity with Reinforcement Learning, a comprehensive case study of FinSafe Corp's intrusion detection system. Reinforcement learning is revolutionizing cybersecurity, particularly in the realm of intrusion detection systems. Imagine a large financial institution, FinSafe Corp, which is continually under threat from sophisticated cyber attacks. FinSafe Corp's network team, led by the seasoned cybersecurity expert Dr. Emily Chen, recognized that their traditional IDS was no longer sufficient to counter the escalating threats. Dr. Chen proposed the integration of RL into their IDS to enhance its adaptability and real-time response capabilities. FinSafe Corp's network is vast, comprising thousands of devices generating terabytes of data daily. Traditional IDS, relying on static rules, struggled with high false positive rates and missed many novel attack patterns. The team decided to implement an RL-based IDS, envisioning an adaptive system that learns from historical data and evolves with emerging threats. They began by training an RL agent using a comprehensive dataset labeled with benign and malicious activities, focusing on patterns in packet headers, flow statistics, and temporal network behaviors. One of the primary challenges the team encountered was defining an effective reward function for the RL agent. They needed a reward system that would prioritize accurate threat detection while minimizing false positives. How should the reward function be designed to balance these competing priorities? The team decided to assign higher rewards for correctly identifying malicious activities and lower penalties for false positives. This approach ensured that the agent was motivated to improve its detection accuracy without overwhelming the system with alerts. Implementing the RL-based IDS in real time posed another set of challenges. The agent had to process incoming data swiftly and adapt its detection strategies on the fly. How can RL-based IDS ensure timely responses to detected threats? The team deployed the agent in parallel with the existing IDS, allowing it to learn and adapt in real time by continuously updating its detection policies based on the latest network observations. This setup enabled the RL agent to provide prompt responses, significantly reducing the impact of potential cyber attacks. The decision-making process in cybersecurity involves critical trade-offs between security measures and operational continuity. Actions like blocking IP addresses or isolating systems must be carefully evaluated to avoid unnecessary disruptions. How can an RL-based IDS balance the trade-off between security and operational continuity? The team trained the RL agent with a cost-sensitive reward function that considered the operational impact of different actions. This training helped the agent to develop strategies that effectively countered threats while minimizing disruptions to FinSafe Corp's operations. Continuous learning and improvement are crucial for maintaining the efficacy of an RL-based IDS. Cyber threats evolve rapidly, and the system must keep pace to remain effective. What strategies can ensure that an RL-based IDS stays ahead of emerging threats? The team implemented online learning techniques, enabling the RL agent to update its knowledge base incrementally as new data arrived. This approach allowed the IDS to adapt to new attack patterns and maintain high detection accuracy over time. Scalability was another critical consideration. FinSafe Corp's network was vast and complex, requiring the RL agent to process high-dimensional data efficiently. How can scalability issues be addressed in RL-based IDS? The team employed parallel training, distributing the learning process across multiple agents and processors. They also utilized experience replay, allowing the agent to learn from past experiences by storing and reusing historical data. This combination of techniques enhanced the scalability of the RL-based IDS, ensuring it could handle the demands of FinSafe Corp's large network. The integration of RL with other machine learning techniques further improved the performance of the IDS. How can combining RL with supervised and unsupervised learning enhance threat detection? The team used supervised learning to train initial detection models with labeled data, boosting the accuracy of threat identification. They also integrated unsupervised learning to identify novel attack patterns by clustering similar anomalies. This hybrid approach provided a robust and comprehensive defense mechanism capable of detecting a wide range of cyber threats. Real-world applications demonstrated the effectiveness of RL-based IDS. For instance, a study by Mustafa et al. Showed that an RL-based IDS could protect critical infrastructure networks with high detection rates and low false positive rates, outperforming traditional IDS. Another study by Nguyen et al. Revealed that RL-based systems could adapt to different attack patterns in cloud environments, maintaining high accuracy in detecting malicious activities. Analysis and solutions. 1. Reward function design. The reward function must balance detection accuracy and false positives. By assigning higher rewards to accurate threat detection and lower penalties for false positives, the RL agent is encouraged to refine its detection capabilities. This balance ensures that the system remains effective without overwhelming users with false alerts. 2. Timely responses. To ensure the RL-based IDS provides timely responses, it should operate in parallel with existing systems during the initial phase. This parallel operation allows the RL agent to learn and adapt in real time, providing prompt responses to detected threats. Continuous monitoring and policy adjustments based on recent observations enhance the IDS's real-time capabilities. 3. Balancing security and continuity. The RL agent's training should incorporate a cost-sensitive reward function that considers the operational impact of different security actions. This approach helps the agent balance the trade-off between security and operational continuity, selecting actions that effectively counter threats while minimizing disruptions. 4. Continuous learning. Implementing online learning techniques enables the RL agent to update its knowledge base incrementally with new data. This continuous learning process ensures that the IDS adapts to evolving threats, maintaining its effectiveness over time. 5. Scalability. Addressing scalability involves employing parallel training and experience replay. Parallel training distributes the learning process across multiple agents and processors, increasing efficiency. Experience replay allows the agent to learn from past experiences by storing and reusing historical data, further enhancing scalability. 6. Hybrid machine learning. Combining RL with supervised learning improves initial threat detection accuracy by leveraging labeled data. Integrating RL with unsupervised learning helps identify novel attack patterns by clustering similar anomalies. This hybrid approach provides a robust defense mechanism capable of detecting a wide range of threats. 7. Real-world applications. Studies have shown that RL-based IDS can outperform traditional systems in various scenarios, including protecting critical infrastructure and detecting DDoS attacks in cloud environments. These real-world applications highlight the effectiveness and adaptability of RL-based IDS in enhancing cybersecurity. In conclusion, the integration of reinforcement learning in intrusion detection systems offers significant advancements in cybersecurity. RL's adaptability, real-time response capabilities, and decision-making prowess make it highly suitable for dynamic and complex cyber threat environments. By addressing challenges such as reward function design, real-time operation, balancing security and continuity, continuous learning, scalability, and hybrid approaches, RL-based IDS can provide robust and comprehensive defense mechanisms. As demonstrated in real-world applications, RL-based IDS are effective in various scenarios, reinforcing their potential as a cornerstone of modern cyber defense strategies.